Welcome to Finite Element Methods. We're in this speaker series where we're going to have experts in the industry coming in and teaching you about finite elements and the things that they encounter in real life. And it's with great honor, I'm going to introduce you to Scott Lee, who is a senior engineer. And he's going to be talking to us about a lot of things. And I'm excited about this presentation because a lot of effort was put into it. And he has a lot of experience. Not a lot of people have the experience he has. He's worked on a lot of different commercial aircraft, and he's worked on engine nacelles, which are quite complicated. And he's actually worked in various military applications, commercial applications, and his expertise really lies into the analyses using software such as Nastran. In this course, where we've been using abaqus, but the ideas apply very much to Nastran as well. And the solutions you see written there are basically static, dynamic, buckling, those kinds of solutions that you're going to be encountering in this course. And it's exciting because we're going to be looking at how to apply those with a different, completely different finite software. And the reason we thought that would be a great idea to expose you to that so you can see that the steps are similar. That once you learn finite elements in a different software, when you go to a different software, the ideas are the same, but the implementation could be slightly different. And we're going to learn a lot from that. He has a bachelor's degree at UCLA from structural engineering. He has a master's degree at USC in aerospace structural engineering. So I don't want to understand how Scott Lee will root for a team, whether he goes for the Bruins or the Trojans when they're going against each other. I assume that half of him is fighting against the other half of him. Regardless, it's exciting to see somebody that goes to both universities and has done really well in that academic arena. He plays one of the things that Scott Lee brings to the table is a work-life balance, and he plays sports, weightlifting, running, and loves podcasts. And he has a lot of energy. I haven't met a lot of people like him. So with that said, Scott Lee, over to you.
All right, thanks for that introduction, Vinay. Just to answer your question, I do root for the Bruins since that's my undergrad school. So there's that. But I'll go ahead and get started. So the main intent of this presentation is to provide a very high-level overview of finite element modeling applied in the real-world environments. I'll go over a quick introduction to FE modeling, some guidelines, tips, and rules will be discussed. And then I'll go over a couple of fairly simple tutorials, time permitting. I have about 7 to 8 tutorials I want to go over. Not sure if I'll have the time to go over all of them, but I'll go over the general process of building a very simple model and let's viewing the results and seeing if the results make sense. And as Vinay mentioned, I will be using FEMAP because that is my go-to tool that I utilize on a day-to-day basis at my work. So next slide, please. So I'm not going to read through this entire paragraph here. You guys can read it over after, whenever you guys have time. But basically, if I were to simplify what is the finite element method in a couple of sentences, all it is saying is that you have a complex domain, and that complex domain theoretically has an infinite number of degrees of freedom. So how can you assess a structure when it has an infinite number of degrees of freedom within the domain? Well, what you do is you want to simplify that domain into simple shapes like squares, triangles, and you want those triangles and squares to cover that entire domain. And if you know how to analyze, the structural properties and the structural equations for that very simple shape, like a square or a triangle, then you can connect all of them together using nodes. And with that, can you go to the next slide, Vinay? You come up with a very large order of systems of equations. And luckily, nowadays, since we have a high amount of computing power, we can solve these large order system algebraic equations fairly quickly. And typically in the finite element world for structural mechanics, the thing that you're solving for is your displacements. We call it the displacement method. And essentially, you solve for the displacements using a solver called Nastran or abaqus, and from displacements, you can calculate your strains, stresses, and your forces. That's a very high-level overview. Those paragraphs kind of go into a little bit more detail. It gives a really good description of what the finite element method is. So in terms of the future of structural analysis and aerospace engineering, nowadays we're going to a pure finite element modeling type of approach within the field. So what I'm trying to get at is, if you want to be successful within this industry, the entire industry is moving towards a modeling based approach. That being said, the main purpose of this slide is to basically state that you kind of need to, or you need to know both. You need to know the fundamentals, the hand calculation methods, the theory behind FEM, as well as the application of FEM. And the reason why I say that is because without knowing the foundation, you're gonna have some issues if you just purely just start modeling things without really understanding the physical phenomenon, the theory behind all of it. Because when you start building models, especially complex models, it is very easy to make mistakes. And so in order to capture those mistakes and in order to understand those mistakes, if you have a really solid foundation of structural analysis theory and hand calcs, you'll be able to spot them very easily. But if you don't, a newer person that doesn't really have a good foundation in the hand calc methods, they may not catch those mistakes, and then they may publish results that are just totally erroneous, and then the results just become basically useless. So that is the main reason for this slide. Is it's important to know both. Don't go all into finite element modeling applications and without really understanding the theory. Okay, next slide. Anybody have any questions so far? Okay, so before I begin, I just want to get on the soapbox really quick, just give a quick speech. If you decide to pursue this type of field, finite element modeling, structural analysis in aerospace, if you decide to join a company like Northrop, Lockheed, or Boeing, it is very important, if you want to be successful in this field, is basically to work hard. And unfortunately, there are no shortcuts in this field. So there's no fast way to become, a highly elite, highly skilled individual in this field. You're going to have to go through the steps and the processes and put in the time and the hard work. And another thing I want to state is it's important to stay humble, because in the engineering field, you're going to make mistakes, unfortunately. Like, I can guarantee you that if you get into this finite element modeling field, you're going to make mistakes modeling. And it is important to always remain humble and learn from those mistakes, and always be in a mindset of learning and trying to be better and learning from your mistakes and learning from others. And yeah, that's just my quick speech there. Next slide, please. Also, in the finite element modeling world, and this actually just applies just to the engineering world in general, is that you're going to get assigned a certain component to analyze. This component is only a small part of the entire system, but this component may be complex in a lot of ways. And so you may be trying to solve this component, and you may be having issues trying to solve this complex component, but it's always important to kind of always try to step back a bit and look at the entire picture. and see how your component is interfacing with the bigger picture, which with, like, for example, let's say you're working on a frame of an aircraft. That frame is connected to the skins. That frame is connected to other, floor beams and so forth. So it's important to always step back and understand how it's interfacing with, your with adjacent structures, and then go back in deep diving into looking at your specific component. Just a general advice. Next slide, please. So I'm pretty sure you guys are all familiar with this. And when you really think about it from a high level perspective, finite element modeling, the process flow perspective is actually quite simple. As I mentioned before, all you need are very simple shapes. In this figure, you see triangles, you see shells, or they call them C-quad fours, or you see hexagonal elements. And all you do is you place those elements into your domain. And in this figure here, you see basically a like a trailing edge, or like a trailing edge type of structure on an aircraft. And you just basically model that entire surface with shell elements, and it may be encompassing some triads as well. And you just stick them all together with nodes. And then what you essentially do is you apply your force, however your force is being applied to the structure, and you apply your boundary conditions. It's ready to run. You run it in a solver such as NX-Nastran, or in your guys' case, abaqus. And then you spit out the results, and you view the results. And the results that you view are the deflections, the stresses, the strains, and so forth. So from an overall perspective, it's a fairly simple, high-level process. Next slide, please. Any questions so far before I continue? All right. So as I mentioned before, I don't want to be a broken record, but let's just say that you have a very simple bracket, as you see here on the right. It's a very simple model. What happens is when you're working in the industry, they're going to give the designer is going to give you the CAD model. And then what you do is you want to mid-surface the geometry. You want to mesh it with shell elements, apply the material properties. For this example, it would be aluminum structure, so it's an isotropic material. Apply the boundary conditions at the 3 top holes. Apply the loading at the end of the flange. Run it in Nastran. Post-process and view the results, deflections and stresses. So this is an example of a very straightforward model. Next slide, please. It can't really be that simple, right? So yeah, that past example was extremely straightforward, but unfortunately in the real world, where you're dealing with complex systems such as aircrafts, which is what I typically deal with, you're modeling entire aircraft systems. You're modeling the wings, you're modeling the fuselage, the skins, the stringers. These structures have extremely complex loading distributions across the aircraft. These models have not 100 nodes, not 1,000 nodes, but hundreds of thousands of nodes, millions of nodes and elements. The load sets, are they a balanced load set? Are they, if they're unbalanced load sets, where are you placing your boundary conditions? You need to make sure your boundary conditions are placed correctly. And for example, you don't want to place too many boundary conditions and over constrain your model, which would make your entire model obsolete and not correct. And in the real world, we deal with global load FEMs. So you can see on the bottom left picture is what we consider a global loads FEM. And what we mean by that is that it's meshed with coarser elements. For example, in this example, I'm just making it up, but it can be like 3-inch elements, 4-inch element sizes. And the reason why we do that is because we can't make the entire aircraft extremely finely meshed. It's just not practical. So we start with a very coarse type of modeling philosophy, make the element sizes bigger, and we call that a loads FEM. And then what we do then is we then create what we call a breakout fine grid FEM. And on the right is an example of a breakout fine grid FEM where it's much more finely meshed, where the element sizes are not 3 inches, they're more like 0.2 inches, 0.1 inches. And in this scenario, we're able to model a lot more details, such as KT features. We're able to model the connections between all the parts in a more finely detailed manner. And what we end up doing is we grab the free body forces from the global loads FEM and we map it to this fine grid FEM. And then in this fine grid FEM, we're able to evaluate the displacements in a more accurate manner, the stresses and strains in a more accurate manner. What do I mean by KT features? Great question. So if you look at that, figure on the bottom right, if you look at that opening, that turquoise color opening, do you see the corners? In the global loads FEM, you wouldn't be able to model those corners very finely. But in this kind of model on the right, it's very hard to see. You can't actually see it. I can't really zoom in, but if you were to zoom in on those corners of that cutout that you see, that turquoise cutout, we can actually extremely finely mesh those corners and get very accurate stress values and strain values at these KT features that you wouldn't be able to get in a global loads FEM. Does that make sense? And I'll actually go over that in a tutorial, actually, in one of the tutorials. Okay, it looks like you got it, so cool.
So there's a question, and the question is, what do you mean by KT features? And I assume that's stress concentration.
Yes, that's correct. Stress concentrations. And those stress concentrations would be like you were pointing at those corners of those cutouts. Wherever you have basically cutouts, wherever you have like these weird stress concentration features that you wouldn't be able to model. Yeah, basically where you have like these tight radii, essentially, yes. You're not going to be able to model that in a global loads FEM where you're modeling with 5-inch elements. So you want to do that in a finer grid FEM. All right. Any other questions before I go on to the next slide? So here are a couple more questions that you need to ask yourself when you're dealing with these complex systems. What is the proper modeling philosophy? Are we going to model with shells? Are we going to model the skins with shells? Do we want to do it with C shear elements? How about the stringers? Do we want to model them with rods or bars? How do we want to interface? How do we want to conjoin different components? Do we want to hard node them? Do we want to maybe spring them off? These are just a couple of questions you gotta ask yourself before starting a large FEM job. How do we distribute the mass across the aircraft? We need to make sure that we're modeling the properties correct. So the thicknesses and the material properties, we need to make sure that those are accurate. As I said, are we modeling all the interfaces correctly? This is actually a major issue that a lot of programs come across is they sometimes don't understand how they're going to model interfaces correctly, and they sometimes screw that up. And when you don't model the interfaces correctly, then your entire load path is erroneous. And sometimes it's just a pure mistake, a pure miss in the FEM. People just don't get that right. As I mentioned already, we should model with the global FEM coarse grid and then create breakout FEMs with finer mesh sizes. Do we have accurate load paths? Do the load paths make sense? And what do the free body diagrams look like? Do the free body diagrams make sense? Any questions before I move on? I'm not going to go into these in too much details, and I don't expect you guys to understand everything I'm saying. These are just examples of questions that I have to ask myself before I start a job. So yeah, so as I move on, these finely meshed sections, they require a lot more resources because it's going to require a lot more labor. It's a lot more labor intensive when you got to finely mesh things. As I mentioned already, KT, stress concentration areas, it takes more resources to model those more accurately. With these breakout FEMs, with finer FEMs, we can run more complex solutions like buckling solutions, nonlinear solutions, and dynamics. We're not just running solution 101 linear static. We can run other complex, more involved solutions. And as I mentioned before, how do we attach the separate parts? Do we want to spring them off with C-bush elements? Do we want to use RBE2s, RBE3s, rigid body elements? Do we want to use glued contacts or just normal surface contacts? Are we sure our load sets are extracted properly from the global FEM, and are they mapped accurately onto the breakout FEM? That's not an easy procedure, so you got to make sure you do all that right. Another big thing is, are we sure our boundary conditions are appropriate? We need to make sure our models are not overly constrained. And what do I mean by that? If your model is overly constrained, you have these very stiff boundary forces that are going to be unconservative to your model, because when you overly constrain your model, you're essentially sucking out all the load, not all the load, but you're sucking out more load than you want to at your boundaries, and less load is going into your domain, into your structure. So your stress levels, your displacement levels, your load levels are going to be smaller if it's overly constrained, and that's not what you want. When you specify loads, do you in general try to input larger loads and apply factors of safety, or try to use accurate loads and apply factor of safety? Does all conservatism only come from factor of safety? So our loads that we apply to the airframe include the factor of safety. So typically from the aerodynamics group, we're going to get a distributions of load across the aircraft. And in finite elements, everything's discretized, right? So essentially what they provide us are either pressurized loads or basically grid point forces. So loading at each of the nodes with a certain magnitude. And they typically apply those with a 1.5 scale factor. And that 1.5 scale factor is basically our factor of safety. All right, seems like I answered your question. Any other questions? Okay, so I'll go on to the next slide. So unfortunately, that simple example I showed you before with the bracket, it's never that easy in real life. And some of the tutorials I'm going to go over are very simple examples. And I'm only going through those because obviously this is an introduction course and I don't have really much time to go over more complex systems. But just keep in mind that the problems you guys are probably going over are more basic, straightforward problems, which is good. That's a good base where you want to start learning these tools and applications. But in the real world, it's a lot more complex. So basically what I'm trying to get at here, it's not as easy as it seems. And I'm going to get on the soapbox once again and basically just state that it does get easier if you put in a lot of time, a lot of effort, and a lot of work. And as most of you guys are familiar with, is a 10,000 hour rule. And unfortunately, like I said, there's no shortcuts in this field. So typically, in order to get at a semi-elite level, typically hitting mastery level in this field is one of those things that are far reaching that you can never really reach because you're always learning in this field. You're always learning new things every single day. And so, but in order to get highly efficient, in order to become more experienced and more accurate in your modeling, you got to put at least 10,000 hours. And the more time you put in, the higher the skill level you will reach. And ultimately, where you want to be at, within 5, 10 years in the industry is you want to be extremely fast and you want to be accurate. What do I mean by fast? You want to be able to solve problems fast. So what I mean is when they give you when you're working on a program, a large aircraft program, and your lead or your manager comes up to you and go, "Hey, we need you to model this complex system. Can you solve it?" And typically they're not going to want to wait a month or 3 weeks. They want to get it solved in a couple of days, in a week, maybe 2 weeks if it's a very complex system. So speed matters, and the only way that you become fast at what you do is just putting a lot of practice, putting a lot of effort, learning, and all that, and also being accurate. It's very easy, like I said before, to make mistakes when you're modeling these large systems. It's very, very easy to make mistakes. The level of detail that you need to have when you're modeling is extremely, you need to be highly focused and highly, what's the word? Just highly focused when you're doing this job, because one little mistake can make your entire model inaccurate. So, yeah, so accuracy matters. The worst thing, and no one's going to bash you on this, but the worst thing is when you present your results after you finish your model to upper level management, to your leads, and they find all these bugs in your model and all the results that you were showing were, basically useless. Um, Everyone's understanding, everyone makes mistakes, but you want to, in the field, when you get better, you want to be able to minimize that. Any questions? When you give your estimate to your manager, do you include a buffer time? Typically, yes. If they say they want it done in like 4 days, I have like a 2x factor to it. So I tell them I'll get it done in 8 days. They don't like that, but it's better to tell your manager it's going to take you a bit longer than saying that you will meet it in 4 days and not meet that. You know what I mean? You got to still, you want to give pushback to your manager. If you think what they're stating to you, like they want it done in 4 days, unrealistic, just be honest with them and just be like, "Hey, I don't think I can get it done in 4 days. Give me 8 days." And then, they can't really say anything, to be honest. They're going to tell you to try to finish it in 4 days. But if you tell them 8 days, they're more understanding if you don't meet the 4-day initial deadline. Any other questions? You have anything to add to this, Vinay, before I move on?
Yeah, I want to say that sometimes we move too fast in this industry, and a lot of errors are made that could be have very high consequences. Sometimes the designs were actually validated and tested, and once the testing was done, there's so many errors that they were exposed by the test, and so a lot of this industry moves really, really fast because of profit margins are required, or you need the capability for some reason really quickly. And so it's important that prior to really providing answers, you can check everything. You can check your boxes and say, my units are consistent, my boundary conditions make sense. I have I have looked at this. I'm an expert at this. I am an expert at this, but I'm gonna have a peer review. I'm gonna have somebody else look over my model because I'm too close to it, and I may not be able to see these errors. And I want to say that working on this, I've made errors myself, and by having others look over my work can be very valuable. And there's nothing wrong with it, and it's something that it gets missed a lot. So that's what I would like to add there.
Yeah, on point, Vinay. I same thing over here where I work. I've made mistakes. We've made mistakes in our models, and sometimes when you move too fast, you can make mistakes, and then it gets costly because you have to go back and fix them. So maybe it was better just to take your time initially to just do it right the first time than having to go back and do it a second time or third time. Yeah, and like I said before in one of my previous slides, it's important not to have a big ego in this field because you always want to stay humble and understand that, hey, you could be possibly wrong or you could possibly be missing something. So you always want to kind of talk it over with other people and have other people look at your work and all that. So okay.
And many errors can happen. Composite ply angles can be off. Material properties could have the wrong units. I can keep going on and on. So
Yeah. Next slide.
I want to also point one more thing. The TA, one of our TAs, and we were actually trying to construct a model for you guys so you can then learn how to do modeling. And it's interesting how we struggled to make sure the units were correct. And it took us maybe half hour to 45 minutes trying to make sure, did we get these units right? Does it make sense? Did the calculations from the heat transfer perspective make sense? And that by itself could have been rushed. But I was appreciative that we did take the time to say, hey, the units make sense for this problem. So something to keep in mind, and I hope you appreciate that as you work through the problems, that a lot of work goes behind each of those problems. A lot of time is devoted to making sure everything makes sense. Okay, that was it.
All right. Okay, so I'll finally get off my soapbox and show you guys some tutorials using FEMAP. Okay, so I'm gonna go over a couple of examples. Here's just a figure of the first example. Just a disclaimer, I'm gonna move kind of fast. I don't expect you guys to follow everything that I'm doing. The main intent of all this is just to show you some of the processes and flows when finite modeling. And feel free to stop me if you guys have any questions, if I'm moving too fast. Here's a figure of the first tutorial. We're gonna be modeling with 10 elements. Second tutorial, we're gonna be modeling a structure with bars. Third figure, we're gonna be modeling a bracket with shell elements. Fourth figure, we're gonna do some dynamic analysis, basically normal modes analysis. Fifth figure, we're going to go over viewing stress concentrations of a plate, and also talking about the principle of symmetry. Sixth figure, we're going to go over a very simple example of a wing box, and just going to show you how to view a free body diagram and if the free body diagram makes sense. Seventh tutorial, we're going to go over composite laminate modeling. And then the eighth tutorial, we're going to go over buckling using solution 105 eigenvalue and also solution 106 nonlinear. All right, so in this first tutorial, basically what's going to happen is you're at work and your boss tells you, hey, I want you to analyze this structure. And the designer gives you the CAD model. And so this is where you're at right now. And like I said, it's never really that simple, but this is just for tutorial purposes. So I'm an analyst and I get this CAD and they want me to analyze this component. How am I going to analyze it? In this case, we're going to go very simply. We're going to model it with 10 elements, which are 3D elements. Typically in aircraft structures, for the most part, we don't really deal with 3D elements too much because we're typically dealing with skins and stringers and frames that are more 2D type structures. But I just want to go over the processes and flow when analyzing a structure. So this is my CAD. I'm going to mesh seed it. Going to give it an element size of just 0.39. That's fine. It's mesh seeded. You can see those white holes. And then the first thing I need is I need to define a material. I'm going to define it with a embedded library material with just steel. And so isotropic steel material is what I defined it by. I gotta give it a property. So this is going to be meshed with 3D elements. So I need to create a solid property, and that property only requires the material. And I created that, and I'm gonna basically, the next step would be to apply loads. So I'm gonna apply some kind of loading on the structure, and I'm gonna apply it on a surface. I'm gonna apply it on this inner lug surface. I'm gonna give it a, let's see here. I'm just gonna give it a negative or positive Z value along this global corner system. So just give it 100 pounds. Oh, not negative, positive 100 Z. So you can see the loading there. This is sort of misleading. The total force is 100 pounds. It's not like each vector is 100 pounds. The total force is 100 pounds along this surface. We gotta apply constraints, right? We gotta figure out how to constrain the structure. So I'm gonna constrain it along this top surface, and I'm gonna fix it. It's gonna be fixed, and you can see that I fixed it. And then I'm gonna go ahead and mesh this structure. So let's go ahead and 3D. Let's go ahead and 3D 10 this structure. So you can see that I've meshed it. I'm gonna hide the geometry, and it's all meshed. Anyways, you can see how it's meshed, and we can go ahead and run it now. So I'm gonna go ahead and show the results. So the first thing I typically check is the displacement. So I'm going to animate the displacement. Let's contour the displacement. So as you recall, I fixed it up here and I applied a Z loading on this surface here. So you can see how it's deflecting. And it gives you the magnitude, 00325 peak deflection at this point. So that looks pretty good, it makes sense. Next thing I usually check is the von Mises stress. And the von Mises stress, this is what it looks like. So obviously the more colored it is a higher stress value. And this is important because you can determine peak stress levels, especially at KT areas, like stress concentration areas. You can see where it sort of lights up. And then in the industry, you can do some durability crack growth analysis at those KT regions. So this is kind of like what the von Mises stress plot looks like. Just basically telling you where the peak stress levels are on the structure for that boundary condition and load. Anybody have any questions before I move on? I know I'm moving kind of fast, so.
Sure. How do you identify and avoid stress singularities? Like where there can be infinite stress if the mesh is infinitely small.
So typically in real life, you never really have an actual structure that you're analyzing. Will always have some kind of radius to it. You never want to actually obviously design a structure with a very sharp crack or very sharp crack tip. So any type of CAD that you get, the designer will always have all these radii and fillets. And so you'll never get a stress singularity in the real world environment. And typically you want to avoid that. And so, like I said, you want to always have stress relievers in your design, like radii, fillets, and so forth. Did that answer your question? So you typically will never see that in the real world environment.
Yes, thank you.
All right, if there are no other questions, I'll go ahead and move on to the second tutorial. So in the second tutorial, it's already solved. It's basically a collection of beams. Thickness is turned on right now. So when I say beams, these are 1D elements. And I have thickness turned on. It helps you better visualize things. And so you can see that I applied loading here, here, and here at 250 pounds. And it's constrained at the base with degrees of freedom 1, 2, 3 relative to this global coordinate system. So let's go ahead and look at a displacement. And I will scale it. And let's contour the displacement and let's animate it. So as you can see, this is basically the behavior of your system based off the loading and your boundary condition. And it does make sense, right? You're going to see your peak displacement of around 0.266 inches at this point here. And we can also view the stress levels within the beams. So we can do, let's see, I don't want beam diagram, I want contour beam levels max, and let's not animate it. So basically what this is telling you is that we're seeing peak stress levels along this beam here at this point of about 9,000 PSI. Also, it's getting highlighted here. So this is also a peak stress area. Let's go ahead and try to visualize that better by turning off filled edges so you can see. So you can see that it's lighting up here and lighting up here. Another thing you can do to validate your model is to look at your constraint forces and see if they make sense. Recall we had constraints at these 4 points here, and these arrows that you see, I know they're not very easy to see. Maybe I'll turn on wireframe. What you see here are basically the constraint forces, basically your reaction forces based off these green arrows being applied at the top. It's basically showing how your system is reacting. Couple of interesting things that you can notice is that this one here seems to have the highest amount of reactionary load, whereas this one back here doesn't have as high of a load. Does that make sense? And why is this reactionary load higher than this reactionary load back here? Well, if you look at the loading, it's not along the center line. It's sort of biased towards the right, if you guys can see that. It's biased towards this end here. So that's the main reason why you're seeing higher loads at this point versus this point. And also, if you look at it from this angle, most of the load is biased towards the front. So of course, then most of the reactionary loads are going to be at the front boundary conditions. So that's another check you typically want to make when you build these models is, are your boundary condition forces, your constraint forces, do they make sense? And in this case, they make sense. If I saw a huge amount of load back here, let's say this was like, 600 pounds, that wouldn't make sense, right? Based off your system that you're looking at right now. So then you would know right away something's wrong with your model, and then you would want to debug it. All right, so the first tutorial, we went over 10 elements, which are 3D elements. The second tutorial, we went over bar elements, which are 1D elements. Now, in this tutorial, we're going to go over shell elements, and that's typically the most applicative, typically what you'll see, the most in the real world, especially if you're in the aerospace industry. You're going to see a lot of shell elements because, like I said before, you're dealing with very thin structures with big acreage surface areas. And the best way to model those are with shells. And so what's going to happen in the real world is your boss is going to come to you and tell you, hey, we have this clip. You get it from the designer and they want this analyzed. They want to know what is the peak deflection and where are the highest stress areas, and will it have enough, does the part have enough thickness to withstand the force? So this is what they give you. Typically you want to mid-surface it because it has a thickness associated with it. Of course, every part is going to have a thickness associated with it. And we can check what the thickness is. It is 2.5. I don't know if you guys can see that down here. It's 2.5. So the question is that in inches or millimeters? I'm just going to give you guys the answer. This is modeled in millimeters. So this is 2.5 millimeters. But it's always important to check your part and make sure you have it in the right units. So when you model shell elements, they're 2D elements. So you always want to mid-surface. So I don't know if you guys saw that. This is the CAD model that you get with thickness. And I already mid-surfaced it, but basically you just as the name implies, you want to create surfaces along the midplane of your 3D CAD model. So you can see that it's now 2D. And within the properties of the shell element, we're going to define the thickness.
I want to take a question, and one of the questions is why not use 3D elements? And the reason is because 3D elements are more computationally expensive, while shell elements can represent the thickness behavior just fine and be able to model bending and loading conditions that you may encounter. Usually you're going to use shell elements for thin structures compared to the width directions.
Yep, that is correct. When you're dealing with very large systems like an aircraft, you don't want to go all 3D, or else your model is going to be very bulky and it's going to be very expensive. What I mean by expensive is the run times are going to be extremely long, much longer than shells. And you have to understand, we're not just running one load case. In aircraft industry, we run thousands of load cases, thousands of different scenarios. So it's very important to have a very efficient model. So I have this already meshed, fortunately, and I'm going to turn off the results. I'm going to turn off the nodes. So this is what it looks like when it's meshed. You can see that they're just basically C quads or C triads. You can see how it's more finely meshed around these circles, and that's because we want to be able to capture the KT stresses around the circles with more finely meshed elements with greater accuracy. So yeah, you can see how they're all modeled with shells. And like I said, we have a thickness associated with them, and I could turn that on, thickness, and you can see that in reality, there is a thickness within your model. And so let's say that in terms of constraints, we have it constrained fixed at these holes. And then we apply a loading along these surfaces here. That's what your lead tells you, or that's what the current domain is. That's where the loading is. This is where the boundary conditions are. Let's check how thick the shell elements are. And it seems that they are also, or yeah, I think we already, I think we measured, right? We measured that on the CAD. It's 2.5 millimeters thick. So that's what we have here defined in the plate property. So this is our system. We're going to solve it in Nastran. And what happens is, first things first, let's check our displacements. That's like the number one thing you always check is you want to check how your body is deforming and making sure, does the magnitude make sense? Let's see, contour, total translation.
There's also a question about whether some elements are rectangular in nature and other ones are triangular in nature. Could you explain what drives one versus another?
Okay, that's a great question.
And
So
once when you can answering that, there's a suggestion that you show the input file that goes into Nastran for one of these models, so they can relate to what we're doing to Abacus, and also the FO6 file if you have it available. If you don't have it, that's okay.
yeah, sure. So to answer the first question, the general rule of thumb is you do not want trias in your model. And then you might ask, well, what's wrong with trias? Trias are bad for models because if you guys go into the theory of finite elements, they're called CST, constant strain triangles, or constant strain elements. Basically, they are overly stiff. And I think, Vinay, if you want to chime in, and you can probably explain this better than I can, because triads have 3 nodes. The shape function has like an equation polynomial of like a plus bx, I believe. And then so when you take the derivative of that, your strain is always a constant. Vinay, maybe you can explain that better if you want.
Yeah, we're going to go into that more, but basically the strains are going to be constant. And so if you have one section in compression, one section in tension, the triangular elements it cannot represent both at the same time. It's going to elect one or the other. So you may get oscillations. In this model, however, we see that we have some triads, but for the most part, it's quadrilateral. So it should be so-so. It's okay for what we're doing here. There's more of an illustration purposes, but great question, and we appreciate that.
Yeah, great question. So in the real world, if I saw this mesh and I was the lead, I would reject it right away because it's not a clean mesh. You can see here, this is not clean. There's trias, I could see a lot of trias that can be deleted if it's meshed more cleanly. And if you want to mesh it more cleanly, you got to spend more time, unfortunately. So the cleaner the mesh, the more time it takes to create a cleaner mesh. If you just want to do a very basic, tell the software, hey, mesh this without cleaning up your geometry, it's going to include trias because based off the domain, based off your structure, the system is going to just kind of want to fit in trias because it's just easier to fit in trias than trying to make it all quads. And then the second question and third question, I'll go ahead and show a PDF. Let me go ahead and export this as text. Go ahead and show that. So, let's see. So all this in this model is all written out to a deck, an Nastran deck. I'm not going to go everything in detail, but basically this is calling for solution 101. What outputs do you want outputted when you solve? I want the displacements. I want the constraint forces. I want the internal forces and the elements. I want the stresses in the elements. Here's my SPC1 card, which is I'm going to equal to basically going to call out the SPC1 and load 1. And then we move to the begin bulk. We have these various parameters. We have some coordinate systems defined. And then here we have our force vectors. applied on nodes, and it's called 1, and that's why this load is called 1. And if I could go to SPCs, and these are my constraints, 1, 2, 3, 4, 5, 6, along each of these nodes over here. This is your nodes that we're applying the SPCs on. And we don't have, and then these are your, so those are your SPCs that I showed. Here's your P shell property card. Here's your mat card. We're defining them with aluminum. And then here are all your grid point cards, where they're located in space. And then your C quads and C trias, how they're connected. So what you see, what you guys will see in abaqus is fairly very, very similar. The differences are going to be basically up here, like how it's defined up here is going to be slightly different. Your params may be slightly different, but all of this is typically the same. And I will go ahead and run this. Let's see, I think I can. I'll go ahead and run this. Analyze. So right now, I basically exported that file that I just showed you, the Nastran input file, and right now it's running in Nastran right now. I hope it runs. It's saying that it's not for some reason. Maybe it did run. Let's see. This is your FO6 file. Okay, so yeah, it did run. So this is what you get in your FO6 file. Let's see. And obviously not going to go through all this stuff, but I know it ran because it's giving me an O load and SPC forces, and I don't see any fatals. If you see a fatal message, then that means your Nastran deck had some issues. All right, so in this next example, I'm going to go over solution 103 normal modes. And basically what that is, first I'm going to show you guys what the structure looks like. Okay, so you're working and you're a dynamicist. Let's say that you're working at SpaceX, or you're working on some kind of rocket. They're gonna ask you to perform some type of dynamic analysis, and the first thing that they always ask for is what is the normal modes of your structure. So let's say we have this very simple type of bracket, and your lead is asking you, define the normal modes. Can you tell me the normal modes of this? And that's what we're gonna solve. So let's just say that I already have it meshed. I already have the mass defined on the structure, because you need mass, right, to determine the normal modes. Remember, natural frequency equals square root of K over M. K is the stiffness of your system, and M is the mass of your system. Let's say I fixed it at these 4 holes here. And for normal modes, you don't actually apply any forces, right? It's a non-forced system. It's just a natural frequency of your system. What is the natural frequency of a system based off your mass and your stiffness? There's no loads applied. I just want to make that very clear. And I go ahead and solve it. I do solution 103 and I solve it, and boom, it gives me 10 modes. The first mode is this guy here. And I can actually plot the translation. And keep in mind, these are not real translations. These are basically scaled, like unit translations. Like basically what I'm trying to get at is you can't say this is a 9-inch deflection. It's all unit. It's all scaled by unit scalar factor. Maybe Vinay can explain that more, but it's all relative to a unit vector or unit scalar value. So this is normal modes 1. So you can see that that's the natural modal shape of your system. and the frequency is 89 hertz. So just to refresh your guys' memory, the terms nature and natural are unified by one definition. Let's actually go here. What is a natural frequency? An object's natural frequency is a frequency or rate that it vibrates naturally when disturbed. Objects can possess more than one natural frequency, and use harmonic oscillators as a tool for modeling that natural frequency of a particular object. So this is the first mode. This is the second mode, 208 hertz.
Why is it useful to know this mode?
And this is the third mode. Okay, so why do we want to know these modes, and what's the usefulness of these modes? That's where we need to start talking about the effective modal mass participation factor. And what that essentially is represents the percentage of the system mass that participates in a particular mode. It provides a measure of the energy contained within each resonant mode. A mode with a large effective modal mass participation factor is usually a significant contributor to the dynamic response of a system. So what does that mean? What does all that mean? Let me explain. So what you see here plotted is, let me take that out. So what is this graph telling us? I want to know at this specific node, this node here, which is like this, some node on this structure, what is the effective mass participation factor for each of the eigenvalues? So recall we had 10 normal modes that we solved for, and we want to know how much each of those modes contribute to the total effective mass participation to the overall system as a whole. And these are all in different directions. So this green is Y. So Y meaning the modal mass participation in the Y direction, modal mass participation in the X direction is X, and then this purple is Z. So that's why we have 3 separate graphs for each direction. And the main intent of this is just to show that normal modes 1 is capturing about 40% of the total mass participation and around 55% of the overall system for T2 and T3. Whereas for T1, most of it gets captured at normal modes 3. So you can see this big jump here. Most of that mass participation factor for that specific direction gets captured at eigenvalue 3. And what this is telling us is that the total summation, it converges around 4 to 5, basically around 4. It hits close to the 1, which is your total mass effectivity. So what this is basically telling us is that our main frequencies and our main modal shapes that we want to concentrate on is 1, 2, 3, and 4. We don't need to worry about 5 through 10 when we assess our system from a dynamic perspective.
Another question that came up is, if you want to change the modes of the system to avoid resonance, what approaches are handy or available to you to do that?
That's a great question. So one thing you can look at is something called strain energy, okay, for each of the modes. And so let's say your normal mode's frequency is at 89 hertz, right? And let's say that your forced vibration application on your system is 89 hertz. That's obviously not a good thing, right? Because then we start getting into resonance. We start getting into that phenomenon called resonance, right? We can apply an unnatural or forced frequency to an object that equals the natural frequency of an object. In cases such as this, we are in effect creating resonance, oscillations at the object's natural frequency. And this is not a good thing because you get increased in magnitude of oscillations, which will result in structural failure. So what do you typically want to do in that scenario? your boss tells you, hey, we have a forced vibration at 89 hertz, we're gonna hit resonancy, fix your design. What is your natural frequency equation? Square root of k over m. So you can play with two factors, right? You can play with your stiffness of your structure or the mass of your structure. But the mass is typically fixed for the most part. It's just going to be the mass of your part for the most part. So the main thing you want to the main toggle, the main knob is your k value, right? So either you can increase your natural frequency. So if you want to increase your natural frequency, you want to increase your stiffness, right? So in what ways can we increase our stiffness? One thing is we can make potentially our boundaries stiffer, but in this case, we've already fixed at 4 points. So the other thing is you can look at the strain energy density, and you can see how it's highlighted at these points here, like at this radii here. And you could make it thicker. And when you make it thicker, your strain energy density, or your, let's see, how do we, basically you'll make it thicker and your K value will become stiffer, and you'll basically be able to have a higher natural frequency value. Anything you want to add to that, Vinay?
You can change the materials as well. You can modify the geometry. You can put a support like a strut. So a lot of ways to go about this, but you have the right idea. We want to avoid natural resonance, but resonances that could occur when the forcing frequencies line up with the natural frequencies.
Yep. Thanks for that assistance, Vinay. Those are all good ideas also. Okay, okay, so in this example, we're gonna go over the concept of symmetry, the concept of KT, stress concentrations, and the concept of von Mises stress versus max and min principal stress, all right? So in reality, let's say we want to analyze a flat plate and we want to know the stress concentration levels around this hole. This is what they give you. In this scenario, you can model the entire plate, but let's say that you have a very complex system and you don't want to model the whole thing, and that system is symmetric in this line and in this axis. You don't need to model this entire plate. You only really need to model one quadrant. And that's what we did here, is we modeled one quadrant only. And what we did is we applied symmetric boundary conditions along these edges. And our loading is also going to be symmetric. We're not going to apply the full loading. We're going to apply basically half the loading. Does that make sense? Basically, what I'm trying to get at is when you're modeling very complex systems, if there's a way to do it faster, do it faster. And if your system is symmetric, only model either half or a quarter of your system so that you don't need to waste time with meshing with higher element counts, higher node counts, and higher processing times. Because recall, higher elements counts, higher node counts will be higher processing time, so you gotta wait longer, and it's gonna, yeah, that's basically it. It's just gonna be more expensive to carry around. So just want to go over that. And then I'm gonna move on to stress concentrations. Does anyone have any questions on symmetry, the concept of symmetry? All right. So in this case, I'm actually applying a compressive load. So you can see the green arrows, it's actually going towards the plate, not away from the plate. So it's compressive. And let's check the deformation. And you can see how it's deforming, right? That's nominal and it's compressing. Nominal, that's compressing, all right? I'm gonna hide the forces now. So this is the deformed shape. And the question is, okay, let's view what the stress concentration levels are. So let's go to contour, plate. Let's go through the concept of von Mises stress first. And So notice here that the max von Mises stress is 3000 psi, located at this point, located along this element here. My question to you all is this value a compressive value or a tension value? Are we in a state of tension stress or in a state of compressive stress? Anybody want to give an answer?
I would think compressive, but von Mises doesn't necessarily tell you that, right? Or,
Yep, that's exactly, yeah, good job. Yeah, you got the answer right. It is in a state of compression. So why is von Mises giving us a positive value? Recall that von Mises stress is a scalar value, okay? It will always be a positive value. And it's a combination of your sigma x, sigma y, sigma z, tau xy, tau yz, and tau zx. And so just always remember that if you plot von Mises stress, you don't know whether it's in a state of tension or in a state of compression. The only way you know is when you plot plate top major principal stress, and that will give you the max tension stress field. And you can see that the max tension stress field is actually here. And it's a value of 1000 psi in a state of tension. And that makes sense, right? You guys can look at how it's deforming. This point here is in a state of tension, whereas plate top minor principal stress, you can see that this value correlates well with that von Mises stress that I pointed previously. And this tells you specifically that yes, at this point, we are in a state of compression at around 3000 psi. So like I said, just be careful in the real world when you're plotting von Mises, when you're plotting major and minor principal stresses. Any questions before I move on to the next? I think there was a question.
It's a comment that we need to be careful with von Mises. It's good to plot multiple metrics. And I do recommend max principle when you have brittle type behavior. Von Mises also can be looked at, but you should look at different theta criteria and the most appropriate for the situation.
All right, so in this example here, we're going to do a very simple free body diagram. So this is an example of a wing box. Okay. And this is the tip, outboard tip of the wing, and this is the inboard where it interfaces with the fuselage. It's a very simple example. It's made up of shells and bars. And the way we can see that is if I turn on the thickness, you can see these lines here. Those are bar elements. And then obviously these squares are shells. So it's a combination of shells and bars, a very simple loads FEM type of representation of a wing box. So in this example, I want to go over the importance of free body diagrams. Why? Okay. So let's look at our loading and our boundary conditions. So basically what this is saying is that I have around 250 pounds times 3 that are being applied at each of these nodes times 6. So 250 pounds times 6 being applied along these nodes, this edge. And then on this side, we have all these nodes here. They're all constrained in the 1, 2, 3 global corner system, okay? So first things first, let's check the deflection always. And I know I sound like a broken record here, but that's always the first thing you got to do, deflections. Let's go ahead and hide the boundary conditions and see if that makes sense. Looks pretty good. Looks pretty reasonable. Next thing I want to do is I'm going to turn that off. And what I want to do is I want to plot the total constraint forces. Okay, and see if those make sense. I know it's not easy to see. Let me wireframe this. Okay, that's easier. So what is this telling us? Do you guys see, you guys can see this? Like, recall we had SPCs here, right? And so basically what these are the resultant constraint forces at these nodes. And so what is this telling you? The first thing I noticed is that the force vectors up here are going in the positive z direction, and the force vectors down here are going in the negative z direction. So what that tells me is that based off the loading, we essentially have a cantilever beam, right? What this is saying is that this upper skin region is going to be in a state of compression. And then this lower skin zone is going to be in a state of tension. So just imagine it as a cantilever beam where you apply loading here, you fix it here, and so you're going to have a compressive state on this end and tension state on this end. And that's what this is free body diagram is telling you, is that it's reacting compressive load up here and tension load down here. And it's also telling you that these middle nodes aren't reacting as much. It's really these top and bottom reaction forces that are reacting most of it. And yeah, and if you wanted to do a summation, you can do a free body diagram summation force. So let me turn that off. Let me turn off contour. Let's just do a quick free body. Let's see if I have that. No, don't. Oh, I just need to show it. Okay. Let me show this one. Okay, so what I'm doing here is I'm activating these groups of elements that are yellow, and my activation nodes are these nodes up here. Basically the nodes where the boundary conditions were applied. So I'm basically taking a section cut where our boundaries are. And the thing I'm checking is, does the total summation force of 250 times 6, is that getting translated across all the way across? And you can see it is. So 250 times 6, 250 times 3 is 750, times 2 is 1500. So a total summation force of applied force is 1500 pounds here. I took a free body section cut along here by activating these elements and activating these nodes. And I asked for a total summation force, and it's giving me a 1500 pound downward force, which is basically reacting this upward force. So I know that this applied force is getting translated across this wing box, and it's getting reacted out here. And that's just an important check you typically want to make with your models, is you want to make sure that these kind of free body diagrams, they make sense. I could also plot the moments as well. So you can see here that I have a moment of 135,000 inch-pounds. You guys see this green arrow here? 135,000 inch-pounds. How do I calculate that? Well, the distance between this end and this end is what? 90 inches. You guys see that? 90 inches between this point and this point. So if I bust out the calculator, and so 1500 times 90 is equal to 135,000. That's your moment reaction. This is 1500 times that by 90, which is getting reacted at this interface here. So those are just important checks you want to make, and make sure those make sense. Any questions regarding this? I'm going to turn off this one. So essentially, we have a shear force reaction and a moment reaction being reacted by these applied loads. This is your free body diagram. Not only that, you can actually take section cuts along this entire wing, and you can actually plot out your shear moment diagram across this wing by taking multiple free body section cuts and just plotting out the shear and the moments. I didn't do that here, but you can do that. And let me turn this off. So what you see here is essentially a very simple plate with shell elements meshed, and I fixed this in and I applied a 1,000 pound total load along this edge. Now, instead of meshing it with a metallic property, you'll see here that first I created a material property for a glass epoxy type of lamina. So you can see here, I'm using a glass epoxy, and these are the stiffness and shear E1 and E2 of your lamina, material properties. And then what I did was I created a layup. And in this instance, the first one, I just created a layup of 1 ply. So 1 ply of that material that we created here, and that thickness of that 1 ply is 0.125 inch. I'm gonna say millimeters, but yeah. And the angle is 0 degrees. Okay. So one thing you always need to check for your elements when you do laminate composite modeling is what is your element material direction. And so you see these arrows here? That defines your 0 degree direction. So I'm basically stating that for this layup, I have the E1 direction going along this flow here, along this kind of like the Z axis. All right. That's how the material definition is defined. I can define the material direction in the other coordinate system as well. I could easily define that by modify, update elements, material orientations, and I can do it along a vector and just do it along the x vector. So this x vector here. And now if I check my material directions, that should not happen. Let me Control Z that. You can see I modified my 0 degree coordinate system to be along this x axis. So that's very important. You always want to define that in the correct orientation because that defines your 0 degree direction for your lamina. Okay, so I'm gonna plot the deflection of just the 1 layer. This is just the 1 layer, okay? It's just this guy, 1 layer. And you can see that it's planar. You don't see any type of out of plane type of deflections, right? But let's say that I define the laminate as a 0, 90, 0, 90. So it's no longer defined as a 1 layer, but it's defined by 4 layers. And the layers are 0, 90, 0, 90. Let's plot the deflection of that. So does anybody know why, just give a guess, why for 1 layer, it doesn't have any type of Y deflection, but for a 4 layer, that's 0, 90, 0, 90. When I just pull it in the X direction, it's also displacing in the Y. Does anybody want to give that a shot? I don't know if any of you guys took composites, but let's look at the Abd matrix of just this 1 layer laminate. Okay, I'm going to compute the Abd matrix. So this laminate consists of 1 ply, total thickness is 0.125. Here is your in-plane properties of your laminate, which will match your lamina because it's only 1 ply. And look at your Abd matrix. I don't know if any of you guys took composites, but notice that your B matrix is 0. And that makes sense because we only have 1 ply, so your laminate is symmetric. Now let's check our 4 layer laminate. There's 4 layers. Let's compute the Abd matrix. So in this instance, we have 4 laminas representing the laminate. So 4 plies, total thickness is 0.2. And so these are your laminate modulus. And the thing I want to highlight is this. You have your B matrix is no longer 0 for B11 and B22. Why is that? A 0, 90, 0 is not a symmetric layup. This is not symmetric. 0, 90, 0, 90. It's not symmetric along the midplane. So because it's not symmetric, your B values are populated. It's the B matrix is essentially a coupling between your extensional stiffness and your rotational stiffness. It's a coupling between the two. So when I say coupling, when you apply, like, let's say a axial load on your system, like I have here, not only is it going to extend axially, but it's also going to bend. And that's what you see here going on. That's the reason why it's bending. In a composite laminate that's not symmetric, you're going to see a coupling behavior of your displacements with axial and bending. Does that make sense? So the main intent of this tutorial is just to go over the material properties of composites, the lamina, how you gotta create, you need to create a property for your composite laminate, and in your laminate, you need to define a layup, whether it's one ply, which is typically never the case. You're gonna have more than one ply, so this is typically the case. And a good design would have made it 0, 90, 0, 90. And in this case, it's a symmetric layup, and I can compute that. And we will see that our B matrix is 0. So essentially, if our laminates was 0, 90, 0, 90, our B matrix, our laminate is symmetric, our B matrix will be 0, and we will not be seeing this type of coupling anymore. We will see something more like along this direction, just pure laminate extension. All right. Any questions before I move on to the next tutorial, or do you have anything to add, Vinay, to this?
I think it's very important to check ply angles. I've seen a lot of designs where that was not done, and it led to some issues in the design process. So important to check ply angles, making sure you have the properties measured from test data, that you have a good database so they can have confidence in the modeling techniques. Also, test validation of these models is recommended.
Yeah, composites is a different animal, so got to treat composites a lot more differently than metallics. And this is the last tutorial, and what we're going to go over is buckling. And essentially, what we have here is a system of bars. I have thickness turned on. It's really bars. And I have thickness turned on just for better visualization purposes. And you can see here that I constrain these bottom nodes. And just think of this as some kind of tower of some sort, right? It looks like a tower. It's constrained at these bottom nodes, 1, 2, 3, 4, 5, 6. And I apply loading at these top corner nodes. Your boss comes up to you and tells me, does this system buckle? There's two ways of solving it. There's a solution 105 eigenvalue solution, which is a linear buckling analysis. And there's a solution 106, which is a nonlinear large displacement analysis. The first one I'm going to show you is a solution 105 eigenvalue analysis, linear eigenvalue. And essentially, all you do is you input this, create the input file for this model, and you run it with solution 105, not solution 101 static linear. And the result is this. It gives me an eigenvalue of 0.8. And this is the deflection mode of the system. I don't know why it's not deflecting more. It should be moving. Don't know why. I guess it is. Let's see why. Okay, I guess it is moving, but not as much as I would like. But let's see. But anyways,
So to confirm, these are beam elements and you're showing the cross section, or this is 3D-dimensional elements?
these are beam elements showing the 3D cross section, and it's amplified by quite a bit. So I'll do this amplification, but basically it's telling you that this is the mode shape of the way it wants to buckle. And it's telling you it's giving an eigenvalue of 0.8. And if the eigenvalue is below 1, that's not a good thing. It means your structure is going to buckle under the given load and the given constraints. So either you need to stiffen up your structure, and for the most part, you got to stiffen up your structure, add some material to get this value above 1. So that's the linear solution 105 method. And so this one here, I don't know why the other one wasn't deflecting as much. Didn't make any sense. Okay, maybe, okay, there we go. Maybe this is better. So, okay, sorry. Let me go back to the first one. The first thing you always check is solution 101. When you run solution 105, it actually runs solution 101, and then it runs solution 105. And you can see that in solution 101, it's not going to evaluate for buckling. That's not what it does. It's just going to evaluate for static linear 101, and this is the way it's going to deform. Right? And then this is the solution 105 run results. And it's telling you that, hey, yeah, it's going to buckle. The other way you can model is using a solution 106, which is nonlinear. And what we're doing here is a couple things. We're enabling large displacement is enabled. Solution 101, large displacement is never enabled because it's a linear static solution. So you cannot model large displacements. But solution 106, you can. And another thing is we're actually loading this in increments. What I mean by that is we're not applying the total force. Let's say it's 100 pounds. We're not applying that 100 pounds right away. We're applying it in increments. Increments of 10%, 20%, 30%, 40%, 50%, 60%, and so forth. Okay. So we're applying it in very small increments so that we're able to capture the large displacement effects if they were to occur. If you were just to apply it all at once, you wouldn't be able to capture all the details of the large displacements. That's why you got to apply it in smaller increments. And so that's what you see here is it's being applied at 10, 20, 30, 40. It's moving kind of fast, but that's what you see. It's being applied in increments, 20%, 30%, 40%, 50%. And then finally, the solution starts to go unstable at around 84%. And we can actually chart that. So here, what you see here is essentially, what you see here is a load factor. And like I said, we load it at 0%, 10%, 20, 30, 40, 50, 60. Basically, we're loading it in 10% increments, okay, of the total load. And displacement, we're trying to capture the displacement of one of these top nodes. So like, let's just say this node here, where it's being loaded. We want to capture the displacement of this node relative to how we're loading the structure, okay? And so what you see is that as we're applying the load in increments of 10, 20, 30, it's displacing in a linear fashion, right? But right at 80, we start to see this weird phenomenon, right? Where it's no longer this node here is no longer displacing in a linear fashion, but it's starting to go in a asymptotic level. So that's basically telling us is where the system is going unstable, okay? It's going unstable right before it turns asymptotic. So let me slow it down for you guys. So 10% load, 20% load, I'll slip to 50, 60, 70, 80, 80% load. And then what's happening is the solution starts to become more and more unstable if you guys are viewing this. And the more unstable it becomes, it starts to basically give out finally as you keep applying higher load increments. And essentially this range here, like 0.8125, that is your capability, meaning the capability of the structure is 81% of the total load that you applied. So the total load that I applied was 100 pounds. It's telling you that it's going to fail at around 80, 81, 82, 82 pounds before it gives out. So the linear solution is giving us a value of 0.8. And this nonlinear solution where you start to go in load increments, it's pretty close, right? It's not too far off base. It's 0.82. So it's a little bit different. You would expect some differences because it's not running in the same type of solution, but this linear eigenvalue solution is giving you a very good first basis run. And if you want to fine tune your analysis, you can run nonlinear and get some more fine tuned values results. Any questions? That's really all I had, Vinay.
That's really good. I appreciate Scott for going through all these tutorials. And I think the goal here was not for you to learn how to use a FEMAP software, but to more kind of learn how to interpret the results. And you can see the critical thinking that Scott has applied to each of these models, trying to interrogate and kind of understand what is going on in each of these models. And we looked at composites, buckling, a plate, a 3D structure, things like that. And in every single one of them, you could see the care he was taking in trying to understand and interrogate the results and figure out, do the results make sense? And you can see for one of the models, whether that occurred planned or not planned. For one of the models, he questioned the results and even told us, "Hey, I'll get back to you. I'm not sure if those results for that clip make sense." And so I think that this is the kind of thinking that we want to apply when it comes to finite elements. Critical thinking, making sure that we understand the results, that we know what we're trying to do, what solution procedure to use, and how to approach the problem. So really nice. I really like the focus on the post-processing because that's one aspect that's not really usually not talked about very much. So this was really, really helpful. So with that said, thank you very much.